all our other programs were stuck during the COVID pandemic situation. So at that time, we started the webinar series, and we could successfully complete 46 webinar sessions, and now we are on the 47th session. And today, I hope we have few new participants also. So I would like to give you few instructions before handing the mic to Shadil sir. So the instructions are: please switch off your mic and camera throughout the session until you are asked to switch on. You can switch on your mic and camera when you are asking a question at the question and answer session, or when you are asked to switch on your camera by the coordinators. Otherwise, please switch off your mic and camera throughout the session. And please, you can use the chat window for typing your questions in the chat window. You can type your questions in the chat window during the presentation, and our coordinators will select that questions for the question and answer session, and one of our coordinators will handle the question and answer session. And you, if time allows us, you can ask the question directly to our respective speaker. So that are the instructions, and please don't try to share your screen. In Google Meet, you have a button to present your screen, so please don't try to do that. It will be an interruption when the speaker presents his screen, so please don't try to share your screen. So that are the general instructions for the participants. I hope that we will have a wonderful webinar. And after the webinar, we will have a quiz related to the webinar topic, and we generally conduct the quiz after the vote of thanks of this webinar session. Today, our student coordinators have prepared the questions for the quiz competition, and we will provide the quiz link after the question and answer session, and it will be active only after the vote of thanks of the webinar session. You can access the quiz after by using that link, and the accurate and fast answers will be considered for the prizes. So once again, all of you are welcome to UL Space Club webinar session 47. We have our UL Space Club members and other students are present here. Along with them, our respected veterans from ISRO and our UL Space Club members, and a few other invitees are here. So all of you are welcome again. I would like to hand over the mic to Shadil sir for introducing our honorable speaker. Shadil sir.
In science. Today, we are discussing on entropy. Entropy is the energy system in all the substances, is a physical property, and that determines the energy level of a particles or a substance. And we get an eminent scientist from a premier National Institute of India, that is NISER, National Institute of Science Education Research, Bhubaneswar. So UL Space Club is connecting to major science institutes in India for the benefit of our children, and the scientists from various fields are supporting these kids in a nation building process. The same thing we get motivated in doing so. And today we are sitting in the 46th session of this webinar. And we could proudly say that we are enjoying it and we are thinking about the innovations in the field of these kind of information transmission, or at the same time the students are receiving at a good end. As a result, in this month of this 23rd May, UL Space Club is organizing a space camp at Thiruvananthapuram. It's Kerala Arts and Craft Village. It's an offline program. That May 23rd is the date on which we switched to the online platform. On the same date, after 2 years, we are switching again back to the offline platform at Trivandrum, the capital of Kerala. And that will be supported by Indian Institute of Space Science, Space Technology, IIST Trivandrum, along with Vikram Sarabhai Space Center Trivandrum, Tumba. So we are getting wholehearted support from these science institutions, and we are so happy. And we have selected around 50 students all over Kerala. Especially we focus on the southern district of Kerala, and we are so happy to get good thinking and creative students for the camp. They are also attending today's program. Then I invite all the veteran scientists and students, teachers, and all the community gathered on this online platform for enjoying today's speech on basic science. That's entropy. So our speaker, Avi Kumar, is from NISER, is a reader there. When we extended our invitation, he accepted it wholeheartedly and agreed to interact with our students for the basic concepts in physics. And his academic excellence also be noted here. We proudly introduce him. He's a postgraduate from Indian Institute of Technology, IIT Madras, and it's also a PhD from IISc Bangalore. These two institutions are the main center or the aim of most of the students who are there, who are in search of the knowledge in the field of pure science there, who are gathered here, and most of them are, some of them are watching this program through YouTube. So his research area is cluster formation in colloidal substances and soft matter in homogeneous conditions, and he have attended several programs nationally and internationally and published a lot of papers and guided uh, young researchers. So we proudly welcome today's chief guest, Dr. Avi Kumar, to this forum. Welcome, sir. Along with, we welcome all the veteran scientists, including our mentor, E.K. Kuti sir, Jairam sir, and Rangarajan sir, P.J. Bhatt sir, and a long list of veterans we have here. We wholeheartedly welcome all of you, sir. Along with that, we invite the students who are the real target group of our program. We invite all of you to receive the informations and the new insights into your minds, and that would be a great experience for you. I welcome our honorable guest, Dr. Avi Kumar, to present his views on his concepts. Welcome, sir.
Okay. Good afternoon, everyone, and thank you for the nice introduction, Shadil sir. Actually, I attended, I think, one of your earlier webinars, and quite impressed with it, actually. So you get so many young students to listen to many people in different areas of science. So before going into my talk, actually this is the first time I'm talking to the young students. So far I was teaching master students or PhD students, but school students, this is the first time I'm talking to them. So I actually I'm excited about it, but there is a slightly disadvantage I have with that one, because I might assume that a higher standard because like I'm teaching masters and PhD students. So my request is like whenever you feel that okay you don't understand something, please stop me. You can ask me and I can clarify it. Like so, I try to be try to prepare my talk as simple as possible. But okay, this is a physics topic and also a lot of not so simple concept involved. So it can be a little tough to understand also. So whenever you feel like, okay, you have a question, just stop me and then ask me. I can try to answer that one. So let's now move on to the presentation. So can you people see my screen? Is it okay now? Oh, okay. I think is it okay now? Okay. So let's start now. So basically, I actually choose a topic which is very close to my area of research, but also like for the it's a very basic in physics or something you call thermodynamics and statistical mechanics. And I particularly chose this subject because the concept of entropy has been people have like misunderstood many times, and then this has been actually if you look at the entropy, it's actually a very simple, well-defined quantity, and also like the applicability also is well defined. But somehow like the way people have used the entropy kind of evolved to reach very embarrassing proportions, and many attributes are or many properties are attributed to this entropy, and which is not actually true. This has been done by even from a very date scientists and physicists to a popular science authors and all those things. So I was trying to give you idea of entropy, and then how people misinterpreted entropy, and also at the end of my talk I'll talk about some manifestations. In that part I'm a bit selfish in the sense I talk mostly about my research in that last part. Okay, fine. So let's move on. So, as I said, entropy is a very unique quantity, not only in thermodynamics and statistical mechanics, but perhaps in entire science. So, people have given so many interpretations to entropy, as I mentioned earlier. Not only in physics, people have used it. Even people, as you go on, you will see that people talk about entropy of living systems, entropy of life, and so on. But many of these concepts are actually not correct, or sometimes it's even absurd. So that's what I'm saying here. It's a very gravely misused and misapplied quantity. So many powers are ascribed to the entropy, but none of which is ever justified. People just say entropy can do this, that, and so on. But why it is so, nobody mentioned that part. Okay, and also this is something one of this one is like, okay, entropy is actually equated to time. Like it was initially introduced as time arrow, but even in one of the books, it is written entropy equal to time, but entropy is actually a timeless quantity. And also, like, okay, in general in physics, one of the basic principles of the physics is like the cause should occur first and then the effect will be there. But in the entropy case, like, okay, people have interchanged between cause and effect, so the causality is not maintained. So that's why, like, okay, I thought, okay, I'll give a little bit ideas about entropy to the students here. So the first question is like, what is entropy? So I'm basically going to talk about two definitions of entropy, which are equivalent. Like one is the macroscopic definition and another one is microscopic definition. There is actually one more equivalent definition in the context of information theory, which I'm not going to talk about because it's a little more difficult to understand. So let us stick with these two definitions of entropy. Okay. So the entropy, I kind of assume that you have some ideas about like thermodynamics. So basically the entropy, the concept of entropy came into picture with the formulation of the laws of thermodynamics, especially the second law of thermodynamics. So traditionally, the birth of second law of thermodynamics is associated with Sadi Carnot, who was an engineer, and he was basically studying the heat engines. So he actually did not formulate the second law as such. He was basically studying about the efficiency of heat engines and so on. So this is a typical or a cartoon of a heat engine. So let's say like, okay, you have a beaker kind of thing where you have a fluid, and then okay, the top here, this is like okay, closed with a movable piston. Okay. So initially, like okay, let's say like okay, this is at a temperature 0 degrees centigrade, and then okay, you say like okay, this is the piston is at this level, so you can put a weight here. Okay. Of course, because of the weight, the piston will go down. So here, and then what the heat engine does is we basically want to do some work using this heat engine. So to do that one, you just take this beaker and then put it into a heat reservoir, which is let's say like 100 degrees centigrade or something, and then obviously the fluid is here, which will start heating up. And then the volume increases, then the piston will move up. And because of this heating, the piston will move up here to the level 2. Then, okay, you can like remove the weight and put it here. Then again, okay, you put it back to this insulator at 100 degrees centigrade. And then again, it come back to this original T equal to 0 degrees centigrade and so on. Okay. So this is basically how the heat engine works. This is actually not the Carnot engine because Carnot, what Carnot did is all these processes, he assumed that they are going to be like very, very, very slow. Okay. So like for example, like heating from 0 to 100 degrees centigrade, it happens very, very small, very, very slow, such that okay, every point it will be like the system will be in a quasi-equilibrium kind of thing. So so basically like okay, this when you do this one, there are like 4 processes involved. So what happens is okay, you start with the cold temperature, then okay, you have this isothermal expansion, and it goes to like the high temperature, and then again, okay, it does this adiabatic expansion, go to higher volume at this constant temperature. Then it compresses back because you put it back into the cold reservoir, and then come back here, and then this. Okay. So what Sadi Carnot, when he studied this one, what he observed is basically the efficiency of this Carnot engine. it depends only on this, like the heat reservoir at higher temperature and the heat sink at the lower temperature. So he could write the efficiency as this, and this was basically the maximum attainable efficiency for any kind of heat engines. Okay, so this is what Sadiq Carnot actually did, and then, but he didn't formulate the thermodynamic laws, but later on, these two scientists, this is like Lord Kelvin, his actual name was William Thomson, and later known as Lord Kelvin, and Rudolf Clausius, they actually looked upon Carnot works, and then based on that, they came up with the laws of thermodynamics. Okay. There are basically 3 laws, or if you include the 0th law also, then 4 laws. But the main or the most important law in thermodynamics is basically the second law. And so there was, they basically, Lord Kelvin and Rudolf Clausius, they formulated in slightly different way, but the formulations are actually correct, or equivalent. So what Lord Kelvin said is there exists no thermodynamic transformation whose sole effect is extract to a quantity of heat from a given heat reservoir and convert it to entirely to work. Okay. So what it means is basically whatever the energy you get from the heat reservoir, you cannot convert the entire thing into work. Some energy will be, only some part of the energy will be converted into work. The rest will be given to the heat sink. Okay. That's what Lord Kelvin's statement, and Rudolf Clausius' statement is actually a little more easier to understand in the sense we see it in our everyday life. So he said no process is possible whose sole effect is to transfer heat from a colder to hotter body. Okay, so if you have a colder body, and then you also basically what it means is heat actually flows from hotter body to colder body, not from colder body to hotter body. That's something which we actually observe almost every day, right? So while these two formulations, they look apparently different, but they are in fact equivalent. Okay. And you can actually I don't go to the proof how do you prove these two are equivalent and all those things. You can actually look at any of the thermodynamics books. They will actually give you the proof that these two are equivalent. Okay, but so this is how the second law of thermodynamics came into picture, and there are many manifestations of the second law of thermodynamics. For example, you look at many spontaneous process you have. So let's say you have a gas or a liquid in one part of the box, you have a partition here, and then if you remove the partition, then they will actually go and occupy the full volume. Okay, and it doesn't go back you can wait long enough, but you don't see that this will go back and then get into one half of the box unless you start doing some work on that. Okay. And so this is a spontaneous process. And similarly, suppose you have 2 different types of gases, initially separated into 2 different sides of the box, and then you remove the partition, they will spontaneously mix together. So all this process, if you look at it, they proceed only in one direction. Okay. Unless you specifically apply some work and then make the system to do that one, it doesn't go back in the other direction. Okay. So all this spontaneous process, they proceed in one direction. And somehow Clausius kind of thought about this one, why it is happening, and he kind of came up with this idea that all this spontaneous process, they are driven by a common law of nature. Okay, and to do for this one, he basically introduced this new term entropy, okay, which he defined as a quantity that always changes in one direction in a spontaneous process. Okay. So this is basically like the quote which he said while introducing the entropy. He said, I prefer going to the initial languages for names of important scientific quantities so that they mean the same thing in all living tongues. Okay? So I propose accordingly to call S the entropy of a body after the Greek word transformation. I have designedly coined the word entropy to be similar to energy. Okay, for those two quantities are so analogous in their physical significance that an analogy of denomination seems to be helpful. Okay, this is basically what Clausius said when he introduced the term entropy. But as we go on, you can see that the entropy is not very similar to energy. It's actually quite a different quantity. Fine. So, and while introducing the term entropy, actually Clausius did not really define entropy. What he did is actually defined a small change in entropy for like one specific process, that is like this spontaneous process which is happening in the forward direction. Okay, so the way he defined the entropy changes, like let's say like this dq to be like a positive quantity and a very small quantity of heat which is flowing to a system at, let's say, temperature T. Then he said, when this heat flows into the system, the change in entropy is basically defined by this, like whatever the small change in entropy ds is equal to dq by T. Okay, so you can actually see like dq is basically the heat, so it has the units of energy, and so the entropy are the units of energy by temperature and so on. And there is one major assumption here. It's basically like the quantity dq. Okay. This must be very small because like whenever this dq is transferred into the system, the temperature T should not change. So the dq should be that small. Then only like this equation is what. And yeah, one thing which you might think like why I put a bar in this dq. So basically the change in the heat or the heat given to a system or heat taken from a system, it actually depends on the path. So it's not a differential quantity. So that's why I put the bar here. Fine. So, and also like Clausius kind of told that okay, entropy is a state function. That what it means is I think you are all familiar with the thermodynamic variables which define the thermodynamic state of a system. Like normally it can be like B and E or P, B, T and so on, like three of them. So basically when I say state function, it depends only on the thermodynamic variables. So once I specify like for example P, V and T or like N, V and E, then that means the entropy is specified. Okay. And if I go from one point to another point, it depends only on the points. It doesn't depend on the path. Okay. Here I said the Q, like how Q changes, that depends on the path. But how the entropy changes, it doesn't depend on the path. It just depends on which point in the thermodynamic space your system is. So that's why it's called a state function. Okay. And this basically like since it's a state function and we can actually like take the 2 points in the thermodynamic space. Yeah. You want to ask something? Is there a question? Okay. So since it's a state function, yeah. Okay, just 1 second. Can you see me now? Okay, fine. So, so basically, since entropy is a state function and depends only on the endpoints, you can always, using this equation, you can always calculate like what is the change in entropy using the Clausius expression. For example, like okay, you know like what is the isothermal expansion. So basically like okay, this is ideal gas going from volume V1 to V2 while the temperature being constant. Okay, that's basically the isothermal expansion. So you can actually very easily calculate this. That has to be like R log V1 by V2, where R is the Avogadro's constant, V1 and V2, these are the volume. So you can actually, using this expression, you can always find what is the change in entropy for during a thermodynamic process or a thermodynamic transformation. Okay? So that's what basically Clausius defined. And then the third law came. Third law basically says the entropy of the system at absolute zero is a universal constant. Okay, and this universal constant you can take it to be zero. So we have a reference point now. At zero, we know the entropy is zero. Then we know how to calculate the entropy change during a process between two thermodynamic states. So this basically enables us to calculate the absolute value of entropy at any state point for a system. Okay. So this is what basically you had from the thermodynamics about the concept of entropy, but still there was mystery about entropy, because what Clausius said is in a spontaneous process, the entropy actually increases. Okay, so this was something how can a quantity increases indefinitely and why it is so. So this was a puzzle for the scientists for quite some time. Okay, so and this mystery was actually solved by the atomistic description of entropy. That is basically the second definition I was talking about. And so this was actually provided by Boltzmann. Okay, and I'll first tell you the definitions, and then I'll explain what that definition means and so on. So Boltzmann actually defined the entropy in terms of total number of microstates of the system. And the state of the system is basically characterized microscopically by given, let's say, energy, volume, number of particles, so thermodynamic variables. And the definition is like this one. S, actually K is basically universal constant. Nowadays it's known as Boltzmann constant. And this is the natural logarithm, that is the logarithm to the base E, and W is the number of microstates you have. Okay, I'll come back to the what a microstate means and so on, but let me finish this definition. And Boltzmann also showed that suppose you have a system of particles, you start with any distribution of velocities for these particles, and then you say okay, let me allow the system to reach the thermal equilibrium. So you just keep the system there and allow enough time for the system to reach equilibrium. And then what Boltzmann said is when the system reaches equilibrium, the entropy becomes a maximum. And also the velocity distribution, whatever you started with, that will change, and then it will reach to a Maxwell-Boltzmann distribution of velocities, which is of this form. Okay, and this also this is typical distribution. If I plot it, so this is the along the x-axis velocity, and this is the probability. And then for two different temperatures, you get these two different type of ones. Here T2 is a higher temperature than the T1. So this is what basically Boltzmann said. And in fact, he actually didn't write down this mathematical form, but he basically said the entropy will be proportional to the logarithm of the microstates. Okay, and I'll come back to this one. So now the question is what is a microstate? You said this is basically the entropy is proportional to the logarithm of microstates. So what do you mean by microstate? So let's look at a very simple example, then we will go on to this. Okay, so look at this one. So let's say we have three boxes which I have labeled as 1, 2, 3, and let's say I have 2 red balls. Okay? Now, how many ways I can place these red balls in these 3 boxes? Okay, so see, this is one configuration. I can put one red ball into the first box, another one in the second box, and third one will be empty. And another configuration is 1 and 3 will be occupied, second one will be empty. The third one is like, okay, the first one will be empty, the second and third will be occupied by a red bar, right? So you can have like three different configurations possible if you have like 2 red balls and 3 boxes, and you have to put 1 ball per box. Okay, so each one of these is actually a microstate. Okay, so if you have 2 red balls and 3 boxes, and if you are supposed to do it like this, and then okay, you have 3 microstates. Okay. Now let's say like okay, instead of 2 red balls, I have a red ball and a blue ball, and I have to put like a 1 red ball and 1 blue ball in one of the boxes. So then the number of configuration is even more, because now like these 2 balls, if you interchange, that will be again the same configuration. But now if I have a red ball and a blue ball, this will be one configuration, and I have a blue ball here and a red ball here, that will be another configuration, right? So then okay, each of this will have 2 more options. So you will have, instead of 3 microstates, you will have 6 microstates and so on. Okay, so this is basically like different configurations we have, and like that is basically the microstate. Now the question is, we are talking about like a very large number of particles. Okay, you all know like one mole of any substance will contain a Avogadro number of particles, and we are like talking about typically of that order, like 10 to the power 23 particles. So, and how do we find the microstates for this? Okay. And of course, like when I say like different configurations, if you go back to like our ball and box thing, the way like we put this one is actually it's a if you want to really calculate like the number of configurations and all those, okay, the system has to be like quantum mechanical in the nature. But when Boltzmann actually came up with this, quantum mechanics was still not there actually. And even the atomic structure of particles and all those things, these are not very clear when he came up with this one. So it was not very much possible to do that one. But and also like many times we can actually do all these things classically for the gases and so on. We don't know to really go into the quantum mechanical regime and do that one. Okay. But so then with, as I said, we are talking about 10 to the power 23 particles. So how do we count the number of microstates? It's not easy, it's difficult, but it's doable. Okay. So how do we say like what is microstate in the case of a system of particles? Okay. So now let's say like okay, let's come back to this one. Let's say like we have n particle which is confined to a volume V, and then for each particle, how do you specify that particle? You can say like this particular particle, okay, the position at an instant of time t is given by this position vector. Let's say like okay, this is the origin, like the left corner is the origin of my coordinate system. So then okay, this is given, the position is given by the position vector Ri, the particle position. In addition to that, we need to know like okay, what is the velocity of the particle at that time. So that is this velocity vector. So if we can specify the position vector and the velocity vector of the particle, then okay, I'm actually specifying the state of the system at that instant complete. Okay. Then so I have like okay, again I have so many like n particles, so like I'll have n position vectors and n velocity vectors. So now if we think in terms of 3 dimensions, each position vector will have 3 components, each velocity vector will have 3 components. So like okay, each particle, the state of that particle at that instant of time is given by like okay, 6 numbers, like 3 position vector components and 3 velocity vector components. So basically, if you have like okay, n such particles, then okay, you have like 6n numbers will be there. Okay. 3n position vector components and 3n like velocity vector components. So we can actually define a 6n dimensional space, which is called like phase space in classical mechanics for an n particle system. And then in that space, just one point, like for example, if in a 3-dimensional space, one point you have 3 coordinates. So like that, in the 6n dimensional space, you will have 6n coordinate, and the 6n coordinates will be basically like the 3n position vector components and 3n velocity vector components. Okay, so one point will actually denote that one. Like for example, like you look at a very simple one. You say like I have a particle. My system is actually a one particle which is moving in only one direction. Let's say x. Okay, so in that case, okay, your position is basically denoted by the x, and then okay, every position you will have a velocity which will be again in the x direction, right? So you can actually represent this in a phase space where, okay, in a 2-dimensional space where one axis is x, another axis is v, right? So at any instant of time, you will have a value for x and a value for v. Okay, so that at that instant you can actually like specify this x and v values by a point in this 2-dimensional space. Okay. Then after some time, like okay, the particle moves, you look at that one, okay, it will have a new x and new v. Let's say like, okay, you have this one and then this one and so on. So basically you can connect all these points. Okay, this will basically the trajectory in the phase space, not in the normal space, because normal space, the trajectory is basically like, okay, just joining the position coordinates. Here, okay, you are basically having a 2-dimensional space where one axis is position, one axis is the velocity. Okay, so you will have that one. So each of this point is a microstate, and obviously, like okay, depending on the other constraint, okay, this will not be going around the whole 2-dimensional space, only a certain region. For example, you say like okay, you confine your particle from 0 to n. Okay, then what happens is along this direction, it will like okay, the points will be only from 0 to, let's say like okay, this is L, so it will have only up to here. So like okay, then okay, you have like okay, all these region left of this line, that will be like only the points where the particle can access it. Okay, so depending on those kind of constraints, like what will be the energy, what will like what is the range of this position, or what is the range of velocity, all these things can constrain this to a particular region. But in that particular region, it can go into different points, and each point is actually a microstate. Okay. So, for example, this point is a microstate. This is a microstate for this, and this is a microstate point for this, and so on. So, like now you generalize this to this is just a one particle moving in one dimension. So you generalize this to like okay, 6n dimensional space. So you have a n particle system whose phase space is a 6n dimensional phase space. And there, like okay, every point is going to be one microstate, and you need to count these microstates. Okay? Subject to the constraint, whatever the accessible region, okay, how many points are there, and you know that okay, these are like points. So basically, like okay, if you count them, they are going to be like okay, infinity. So each point in the 6n dimensional space corresponds to a microstate, but okay, then you have infinite number of this. Okay, so how do you do that one? So we need to assign a small volume around each of these points, then only we can actually count them. Okay. So how do I do that one? So basically, okay, we need to take some help from the quantum mechanics. So I'm not going into the details like how exactly like okay, we are going to do that one. But basically, like okay, you can I think you must have heard about like uncertainty principle, which will give you like okay, what should be the delta x and delta p and how it related to the Planck's constant and so on. So you can take help from that one and then assign a small volume to each of these points, and then calculate okay, how many such points or how many such small volumes you have in that region. Okay. Then once you have that one, you can actually do calculate that. You just need to do an integration according to like your constraints. Then you get the the number of microstates. For example, like the number of microstates for an ideal gas of n particles in a volume V and total energy E is actually given by this. Okay. Now, once I know the number of microstates, I can very easily calculate the entropy. I just need to like take K times log omega. So I do that one, I get into this equation. Okay, and why I'm saying that, okay, so this actually gives you the microscopic definition of entropy, S equal to KB log omega. And why this is equivalent to the macroscopic definition given by the course, use this S KB log omega and then calculate like what is the energy change for like non-processes. Then okay, you get the same answer as the macroscopic definition. For example, like okay, this we said, like if I use this expression for the entropy, and then say like there is an isothermal expansion of ideal gas from volume V1 to V2, I'm going to get this, like which is exactly same as what I got from using the closed-use expression. So that way, like these two are equivalent. Only thing is one is just a macroscopic definition, but in the case of Boltzmann definition, it actually goes into the microscopic details, like or like which part of the phase space is accessible and so on. Okay. So yeah, so this is what I was mentioning before. Boltzmann actually didn't write the mathematical form S of K log omega. He basically said like the entropy is going to be proportional to the logarithm of number of microstates and all. Like it was actually Max Planck who wrote this mathematical form in 1901. So this is what he has written. So this is the place where first time this S equal to K log omega or K log W appeared actually in 1901. Okay. And so this is basically the grave of Boltzmann. Boltzmann actually had this bipolar disease. So he actually committed suicide. And initially, there was nothing in his grave. Then I think Einstein and Max Planck, they were like very good friends of Boltzmann. They wanted to make a grave and all those things. And while doing that one day, both said, okay, we need to put something there. And then actually Planck said, okay, we'll put like S equal to K log omega. So that's how Boltzmann get the name for the mathematical expression. In some of the books, actually, you can see that okay, it's written as Boltzmann Planck formula for entropy, I think, because Planck actually wrote it. Okay, this is a little bit from the history side, but let's move on further. So these are basically the two definitions I was talking about. And as I said, there is a very equivalent definition, which will also give you the same kind of answers. It's based on the information theory. Okay, and I'll not go into the details, but if you are interested in okay, you can just try to, for example, Google like Shannon entropy, which will tell you like okay, what form it is and what those things. So, but that is an equivalent definition of entropy. So these are the three equivalent definitions as far as I know. But now let's go into the misconceptions. So why has this concept of entropy been shrouded in mystery? One of the problems is like, in fact, when this entropy came, there was a lot of resistance to that. When the concept of entropy came, a lot of resistance to the concept of entropy itself. Because if you look at the equations of motion, like for example, Newton's equations of motion, they have a time reversal symmetry. What it means is, suppose I know the position and velocity of a particle at some instant t, okay, then I can solve the Newton's equation, go forward in time as well as go backward in time. Okay, so I can actually find the past as well as the present, or as well as the future if I know the present. Okay, that's what the dynamical equations of motion, if you look at it, like for example, like Newton's equation of motion or different forms of that one. So they all have this time reversal symmetry. Okay, but when you talk about entropy, especially the spontaneous processes or many of these natural processes, they have this observed irreversibility. And entropy is something, the quantity defined to be increasing when you have this one. So people were not really ready to accept the concept of entropy itself, because you don't see the time reversal symmetry for this process, the spontaneous process. Okay, and secondly, the word entropy itself. Okay, so if you look at the dictionary definition of entropy, for example, if you like Merriam-Webster or something, then the entropy, which they say the ancient Greek, it means change, or the literal meaning is 10. But if you actually look at the concept of entropy, it's not the change that is changing, and it's not the 10 that is evolving. Okay, it's something, some quantity, which is it is actually purely thermodynamic. Okay, so this is one of the reasons why people took a lot of liberty, because it was not very easy to understand concept. So people kind of thought, okay, I'll interpret it on my own way, and there is no way like people can disprove me. Okay? So many authors, including like a very great scientists like Schrödinger, they used entropy in a very ambiguous way, and which led to like many misconceptions and misinterpretations. For example, like if you look at this, this is one of the papers came in American Journal of Physics by Steyer. So he basically like calculating entropy for evolution. So the way he said is, whenever a species evolves, okay, they I think he said is 100. Yeah, if I remember correctly, but he said is in 100 years, like if an organism evolves, then in 100 years it's 10,000 times improbable that it's the same organism itself. Okay, there will be changes and so on. So then he said, okay, so if my number of microstate in the final one is W or omega F, and the initial one is omega I, and since there is a reduction of like 1,000 times the probability, so I'll say like the number of microstates reduces by 1,000 times, and then using that, and then like the Boltzmann formula, he calculated the entropy and said, okay, the entropy is actually reducing. So he said entropy of Earth's biosphere is indeed decreasing by a tiny amount due to evolution, and the entropy of the cosmic microwave background is increasing by an even greater amount to compensate for that decrease, and so on. And actually, if you look at this one, okay, this is like entirely wrong thing. Like you cannot, or like the number of microstate, that concept itself is not there for like evolving organisms. Okay, so people have gone to that kind of extremes to like misinterpret entropy and so on. And there are many, especially like in many of the popular science books. I'm not going to list out all of them, but a few popular ones I'm going to list out. So one is actually like a order disorder misconception. This is a very widely known one. Even like the order disorder, okay, this is used as a definition of entropy. For example, if you look at Wikipedia, open your internet, go to Wikipedia and search for entropy. This is the definition you get. Entropy is a scientific concept as well as a measurable physical property. So far, it's fine. That is most commonly associated with a state of disorder, randomness or uncertainty, and that part is actually wrong. Okay. So, and this basically comes because of some of the statements made by Boltzmann itself. So, while interpreting the entropy, so he actually, so you can see some of this disorder measured by the parameter called entropy increases with time. Nobody knows for sure why well is going from order to disorder, but this is so. All this were these are basically the quotes from this book. By this Israeli mathematician Aharoni, known as circularity, a common secrets to paradoxes, scientific revolutions, and humor. So there, so you can actually see that there are many such things. If you just open Google and then look at do a search of entropy codes, there will be so many codes which will talk about entropy as disorder. Okay, but one problem is the order and disorder. They are not very well defined. It's very subjective. For example, look at these two examples which we are talking about. See, I had all the particles in the first half of this and then expand this. Obviously, the entropy increases towards this one. This is the maximum entropy state. But to me, I can say this is actually more ordered because this is all the particles are to the one half. Or look at this one. This is two different gases. And this is a mixed one. This is more entropy. For to me, the two different boxes having two different gases is more ordered. Okay, not only subjective. I can actually, as we go on, when we talk about the manifestations, I'll show you that in fact entropy, you call it as a measure of disorder, but it actually induces order in many systems. Okay. So this interpretation, it's not true. Entropy is not a measure of order or disorder. Okay. There are sometimes entropy can increase when an ordered state forms. Sometimes entropy can decrease when a disordered or increase when a disordered state forms. So these both are possible. So it's not a definition of order or a measure of order or a disorder. Okay, that's the most widely used misconception. The another one is entropy as a measure of probability. Entropy is written as K log P. You remember, this is very similar to the Boltzmann definition, but they are instead of P, it was W. That's the number of microstates, and that's a very huge quantity. If you as I said, you have any systems, you have the order of 10 to the power 23 particles, and each particle will have a position vector and velocity vector. And now you look at how many different combinations are possible. When we were talking about just 2 balls and 3 boxes, we could go 3 microstates or 6 microstates. Now we are talking about 10 to the power 23 particles. Okay, that's such a huge number of microstate. And instead of that, people have replaced this with P, which is the probability. And you know that a probability is always between 0 and 1. It's a number between 0 and 1. And then if you put a number between 0 and 1 here, and then you take a logarithm here, so the S becomes negative. Okay? And entropy is defined to be a positive quantity. Okay, so you can see that, for example, in this book, Science and Information Theory by Brille, is written the probability has a natural tendency to increase, so does entropy. Okay, and probability, it doesn't have any tendency to increase, okay, or decrease. The probability is basically defined as just a number for some events. Okay, so there is no natural tendency for that to increase, and so also entropy also, it doesn't need to be increasing all the time. Okay, so this is another misconception you have about entropy. Then people also looked at entropy as a measure of irreversibility. Okay, and and one of the reasons why people did that one is if you know the second law of thermodynamics and entropy is usually discussed with spontaneous process, irreversible process. And also if you look at sorry, there is a typo here, it's actually reversible process. So if you look at a reversible process, the entropy change is going to be 0. Okay, so people have this idea that, oh, okay, I can say like okay, entropy as a measure of irreversibility, and if I increase the entropy, then the irreversibility increase. There is nothing like that one. Only thing is, if it's an irreversible process, entropy increases. Okay, that is delta S is positive, but there is nothing like okay, delta S is more positive. It doesn't means that okay, delta S is or the process is more irreversible. There is nothing like that. Okay, so it's not a measure of irreversibility. Okay, so this is basically like one of the places where okay you can see such kind of like interpretations. Say Lemons, he said like entropy, a measure of irreversibility of the thermodynamic evaluation of an isolated system. Then says the entropy difference between the two states of an isolated system quantifies the irreversibility of a process connecting the two states. So I can say that basically you can say like the irreversible process, the entropy change is positive. That is true, but it's not. There is nothing like a more irreversible or less irreversible. Okay, so it's not a measure of irreversibility. Okay. Another one, okay, this is quite an interesting one because many very well-known physicists actually like okay, talked about this. So can entropy define for living systems? Okay. And many people like, as I said, like Schrodinger, Ilya Prigogine, Roger Penrose, Monod, they all talked about like, okay, can we define entropy for living systems and so on. So, for example, you look at what Schrodinger has written here. So in this book, like what is life, the physical aspect of living cell, there is a chapter there in that he talks about like entropy of living systems. So he said like, what then is that precious something contained in our food, which keeps us from death? That is easily answered. Every process, event happening, call it what you will, in a way, everything that is going on in nature means an increase of the entropy of the part of the weight where it is going up. Thus, a living organism continually increases its entropy, or as you may say, produces positive entropy, and thus tend to approach a dangerous state of maximum entropy, which is death. It can only keep aloof from it, that is alive, by continually drawing from its environment negative entropy, which is something very positive, as we shall immediately see. But an organism feeds upon is negative entropy. Okay? And again, the problem is entropy, by definition, it's a positive quantity. There cannot be any negative entropy. So basically, this interpretation itself, like even it's coming from a very, very well-known physicist, I will say that this is wrong actually, because according to the definition, entropy cannot be negative at all. Entropy change can be negative, but entropy cannot. Okay. And you can see again in this book, if living organism need food, it's only for the negentropy it can get from it. Negentropy is again the weight coined by Boltzmann himself, like talking about negative entropy and so on. So this is what he said, if living organism needs food, it's only for the negentropy it can get from it, and which is needed to make up for the losses due to mechanical work done or simply degradation process in living systems. Energy contained in food does not really matter, since energy is conserved and never gets lost, but negentropy is an important fact. Okay. So, so this is another misinterpretation of like entropy. You actually cannot define entropy for the living systems because, as you know, the living systems are so complex. They will not be. It will be very difficult to like describe the living systems in terms of like thermodynamics and statistical mechanics. It's very, very difficult. Okay, so again, okay, this is a misinterpretation of entropy. And the last one, which I'm going to talk about, is like association of entropy with time. And this actually you can trace back into the Clausius statement. He said like, okay, the entropy of the universe always increases. Okay? So from there, actually people took it up and then put it as like entropy, you can equate it to time and so on. So the explicit here, he didn't explicitly associate time with that one. It was an implicit statement, but the explicit association of entropy with time zero can be credited to Eddington in his book called The Nature of Physical World. Okay? So he says nothing in the statistics of an assemblage can distinguish a direction of time when entropy fails to distinguish one. So he kind of say like, okay, entropy basically means like, okay, you can say like, okay, which way the time flows. And yeah, one of the reasons why like people were kind of so obsessed with saying that entropy and time, they're related, because many of the processes which we see every day, they actually proceed in one direction, like most of them are spontaneous process, which are like supposed to be irreversible. And we have never seen them to occur in the opposite direction. Like, for example, okay, you drop something, like, for example, you drop a glass down and it gets broken. And so you know that okay, this is a irreversible process. You have never seen that okay, this broken piece of glass coming together and forming a glass, right? But this was again, okay, this was one of the problems Boltzmann faced actually when he came up with the idea, because people were kind of, as I said, okay, there is a time reversal symmetry with the dynamical equations, and then okay, this was saying that okay, no, this process will happen only in one direction. So there was a lot of criticisms and objections to the Boltzmann's theory, and that's one of the reasons why he committed suicide also. Okay. So, and the argument Boltzmann was giving is, no, the processes in the opposite direction can happen, but the probability for such reverse process is very, very small. Okay. So if you live for, let's say, like 1 million years or like 100 million years, you might see that the broken pieces of glasses coming together and then forming a glass. It's possible, but the probability is very, 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 very small. So the connection between the arrow of time and the entropy, that way is only temporary, not absolute. Okay. So in our lifetime or in a very reasonable time frame, we see only spontaneous process, and there the entropy increases. So you will see that okay, you can say entropy is associated with the hour of time, but this is only temporary. At some point, okay, the reverse process also can happen, but the probability is very small. Okay, so these are some of the popular misconceptions of entropy. Now let's look at some of the manifestations of entropy. So we talked about like when we were talking about second law and so on. Like these things are basically the manifestations of entropy. Entropy increases. That's why like the gas actually expand to the whole volume, or the mixing happened because the entropy of the total system increases. Okay, so these are fine. Okay, because you can also think about it. Okay, this is actually fine from both the definitions of entropy, like the macroscopic as well as microscopic definitions. This looks fine for me. So let's look at some counterintuitive examples. And here, basically, I'm going to talk about some materials called colloids in this one, and then okay, some of the dynamics in the colloids and or phase behavior of colloids and so on, where entropy actually plays a lot of role. And you will find some examples which is very, very difficult to even believe. Okay. So, let me give you some idea about like what is colloids and so on. So colloids are basically like particles which are like quite bigger compared to the atoms or molecules. So they are like the order of micrometers or like few hundred nanometers. So they will be dispersed in a medium, and the medium can be a liquid or a gas. Okay. Or even you can have a solid medium also, then you have the solid solutions. Okay. And they are everywhere. They're everywhere in nature, like for example, in foams, in milk, in fork, aerogel, blood, paints, your toothpaste, your soap, even your body. Like, so all of these are like basically, most of them are like colloidal suspensions. Okay. So it's like, okay, what you have is that you have a lot of particles, which is homogeneously dispersed in a medium. These are like colloids. Only thing is, these particles are much bigger compared to atoms and molecules. Okay. And why they are more, okay, so like obviously they will have like okay, the interactions between them. So normally what happens is these colloidal particles will be charged particles, so there will be a lot of surface charge, and then okay, there will be ions in the solution also. So like you will have electric double layer thing. So what happens is, let's say like okay, this charged particle is a negatively charged particle. This is the colloid one. The surface charge is negative. And then what happens is the solution has like both positive and negative charges. But because the negative charges here, the positive charges in the solution gets attracted to the surface. So you will have like two layers. Like you will have a layer of negative charges on the surface of the colloidal particles. Just outside the surface, you will have a layer of positive charge. Okay? So these positive charges actually screen this Coulomb interaction. So instead of the normal Coulomb interactions, you will have something called the Yukawa potential. So, so that is this electric double layer interaction. So you have a repulsion between the colloids, which is given by this. Then in addition to that, you will have this van der Waals interaction, which is attractive. So there is an attraction between the colloidal particles because of the van der Waals interaction. There is repulsion between them. So these are like, okay, individually this is like this. And then, okay, you have, if you add this electrostatic repulsion and van der Waals repulsion, you get this one. Okay, this is something called DLBO interaction for the colloids. So as long as the particle doesn't come closer than this, it looks fine. Okay, only thing is once it crosses this, then all of them coagulate and then form just one chunk kind of thing. So there, okay, you lose actually the stability of the colloidal suspension. So generally, like what happens is in the labs and all, like or in whatever products you have, like a paste and all, okay, you will have the particles situated like around this region, so that okay, there will be like then you will have this colloidal dispersion. Okay, so why these colloids are very important? So like they actually like belong to a class of systems which is called like soft condensed matter systems, which are like basically colloids, polymers, liquid crystals, and surfactants. All these things are together called as soft condensed matter, and all of them have some common property. That's why they club together and called soft condensed matter systems. So one is basically like all of them are characterized by the observable Brownian motion. That is like if you look through a microscope, you can see them that okay, they will be like rattling in the in the solution or in the medium. Like you see like pollen grains in some water or something. Okay, if you look through the microscope, you can see like the constant jiggling of this pollen particles. Similar thing you can see in all these like colloids, polymers, your surfactants, liquid crystals, and so on. And one of the reasons why you have this one, the Brownian motion, is like okay, their potential energy, that is the energy due to the interaction among themselves, is comparable to the kinetic energy. Normal atomic and molecular systems, what you see is the potential energy is always quite stronger compared to the kinetic energy. So you don't find much of this rattling behavior or Brownian motion thing. But here, okay, since the potential energy and kinetic energy are comparable, you see a lot of like Brownian motion. And the soft name came because like okay, they are very easily deformable. So you can apply a little bit of stress, they will get deformed. You can see from like whatever the examples which I have given here. See all these ones, it's very easy to deform them compared to the normal solids or like take for example sodium chloride or something. It's very hard to deform that. But compared to that, okay, these colloidal systems, they are very easy to deform. So that is again, okay, this is true for all these soft condensed matter systems. And there is another thing called viscoelastic. So that is basically like these particles or these systems, for some time they behave like solid, like they will be elastic. That is okay. You apply a stress, they will try to deform. But after some time, maybe they will start flowing like a liquid. So they have for some time it will be solid, sometime it will be liquid, and so on. So that is basically called the viscoelastic. Okay, they are elastic like the solid, but they are viscous like the liquid. So that's why it's called like viscoelastic. And yeah, so the importance of colloidal systems when we talk about like physics or like or science is like, okay, if you look at their phase diagrams, that is like, okay, how they changes their phase from solid to liquid to gases. There are a lot of similarities between the colloidal systems and the atomic systems. And the advantage is, if you want to study the phase behavior of atomic systems, they're quite costly. You need to have like very sophisticated instruments. For example, you need to do X-ray sketching or neutron sketching, all those kind of things to study the atomic systems. But colloidal systems, the system size is, or the particle size is quite large. If you look at atomic systems, each size of each particle will be the order of angstroms, like 10 to the power minus 10 meter. But the colloids, it will be like okay, 10 to the power minus 6 meter. So looking at the colloidal systems, experimentally studying it becomes much more easier. Okay. For example, instead of X-rays or neutron sketching, you can actually do the visible light sketching because their length size, their size is quite high. That okay, they are comparable with the visible region of electromagnetic radiation. Okay, so you can even look at through a microscope. Okay, you just put them under the microscope and look through it, and attach a camera to the microscope and then keep on clicking the photos. You can actually get a different snapshot of the system at different times. Then okay, you can reconstruct the trajectory and do that. So studying them is very simple. That's one of the reasons why colloids are quite important in physics or in science itself. And second thing is another interesting property. So now if you look at the interaction, I talked about the LBO interactions and so on. So in general, atomic systems also you have some kind of interactions because of the charge-charge interaction or dipole-dipole interaction, whatever it is. So in general, okay, they will have a very short range repulsion because of the Pauli's exclusion principle. Like it's like two particles cannot overlap, so there will be a very short range repulsion. Then an attraction which will like slowly die down as the distance increases. So this is a normal interaction between the atoms or molecules, and there is no way you can modify this. Okay? It will be like that. But in the case of like colloids, you can actually tune these interactions, whatever DLVO I said, or like you can tune these interactions by many different ways. Like okay, you can choose the particle type, or like okay, you do it in a different temperature, or the solvent you change, the dilated properties of the solvent you change, or you add something like electrolytes, polymers, or even other colloidal particles, or you modify the particles surface by attaching some polymers into that one. So you can actually get into a very wide variety of interactions. Like for example, you can completely screen all the interactions. You can get a hard sphere like this, that is like particles. They will not have any interaction other than that they are not overlapping. Okay, so you can have that hard sphere interaction. You can have hard sphere plus a very short range attractive interactions. You can have that. You can have a very long range Coulombic repulsion. You can have all these different sorts of interaction range you can get in colloidal systems practically. Okay? In experiments in the lab, you can get all those things. So that way you can study different interactions using the colloidal systems. So that's why like colloids are actually nowadays used as a model system to study different physical phenomena, because you can tune all these interactions and get into like whatever interactions you want. So now, so this is basically an introduction about colloids. Now let's come to the manifestations of entropy in this one. So you look at this, like basically whenever you have a liquid, which is this disordered one, but you like lower the temperature, keep it enough time, you go into like a crystal phase, which is a ordered phase like this. And then according to like whatever definition we know, like this is a disordered structure, so that should have more entropy. This is ordered structure that should have less entropy. So if the freezing happens in normal liquids to like solid, is it a violation of the second law? So this was one of the questions which people were asking for quite some time. And then people came up with a possible explanation. What they said is like, okay, whenever the liquid goes to an ordered structure, like a crystalline structure, it releases heat and to the universe. So, and then okay, the surroundings, they get more kinetic energy because of the heat. Then okay, the entropy of the surrounding increases. So the total entropy of the universe increases in that process. So there is no violation of the second law. This was a possible explanation for normal like okay, liquid to crystal freezing. Okay. Then what happened is okay. Then in 1950s, actually 57, this computer simulation came into existence. So this is basically like you mimic the experiment in the computer. Okay. So what do you do is, like, for example, like these people like Alder and Wainwright, they came up with these molecular dynamic simulations. So what they do is basically they you put all the particles in some space. You specify the position and velocities so the particles at time t equal to 0, then allow like solve this Newton's equation of motion. Okay, so what they did is okay, they did use the hard sphere one. So hard sphere ones, it's as I showed before here. This is the interaction. This one, the first one. So whenever the particles overlap, they have a huge deflection. Otherwise, the interaction is 0. So there is no energy. Okay? If they come closer, then also it's fine. Only thing is they should not overlap. Otherwise, there is no energy. Okay? That's a hard sphere one. And so they found that okay, when you do this molecular dynamic simulation, then okay, if you increase the density of these hard spheres, you actually get an ordered crystal. Okay? So you have the liquid or fluid here, and then okay, you increase the density slightly more, then you get the hard sphere crystal. And in this case, it's not releasing any heat to the universe because the interaction is hard sphere. That means as long as they are not overlapping, there is no energy there. So it cannot release any energy to the universe. It just comes over. Okay. And they actually found that okay, they can, in the simulation, you can actually calculate what is the entropy of this system. And they found that okay, this freezing actually happens because of the entropy increases. So this is the entropy-driven freezing of hard sphere, and the entropy in the ordered phase is more than the disordered phase. Okay, and again, people were not ready to believe them. Like okay, they said, "Oh, this must be some mistake which people like Alder and Wainwright is doing in their simulations, or like simulation itself was a new thing." So a lot of skeptics about the simulations itself. So then from the experimental verification came from the colloids. So this Say and Van Wegen, I think this came in 70s, I think. So they showed that okay, the hard sphere colloids actually undergoes freezing as you increase the density. So these are like okay, basically the colloid dispersants at different densities, then it's exposed to the light. You can actually see like okay, initially it's a liquid, then okay, there is a two-phase region coexisting, and then it goes on, and finally like okay, you have the pure like blue liquid, which basically tells you okay, it's a crystal phase, it's a one phase. So these are Bragg reflections. Okay, as I said, colloids are bigger particles, so you can use light for or like light scattering to study the structure. You don't need X-rays or neutron scattering. So these are basically like you get this same color because you have a homogeneous reflections happening. So, so this is the experimental verification of hard spheres. So what the point here is again, okay, the process happens because entropy increases, but not from order to disorder, but it actually happens from disorder to order, and the entropy actually increases. Okay. So this is one of the manifestations of entropy, like entropy-driven freezing. So then let's go to the other one. So this is basically, again, in colloidal systems, you have an interaction which is not an actual interaction. It's an effective interaction, what you say. So what it means is, suppose you have like colloidal particles. In addition to that, you have a second set of particles. It can be polymers, like for example, in this picture, okay, these are polymers. Or you can have a different size colloid particles itself. So then what happens is, surrounding to like every polymers, okay, there will be a region where okay, the center of mass of this polymer cannot enter. Okay, so the polymers, you can actually think it of as a sphere. Let me go to the next page. I think that. Yeah, say you compare this like okay, the polymer as a sphere. Okay, so it's like a sphere, and the sphere maximum, the center of the sphere can come only up to this point. Okay, so surrounding every colloids, okay, there will be a region which you call it as depletion region, where the center of the second type of particles cannot enter. Okay, so when you have like okay, if I go back, when you have like okay, so many such particles, so in essentially if they are like away, this bigger colloidal particles away, so each particle will have this depletion region. And then okay, these particles essentially are getting less space to move around because of this region here. Okay. Now, if two particles come closer, obviously there will be an overlap of these layers. So basically, whatever this overlap, the system actually releases that much of space, extra space for these particles to move around, the smaller particles. Okay, that means your smaller particles are getting more and more space, so they can actually get into more and more configurations. That means more and more microstates, so the entropy increases. Okay, so then because of that, there is an effective attraction between the larger particles. Larger particles tend to come together, and this interaction is basically called the depletion interaction. Okay? And this is purely entropy driven. Okay. And one of the effects of this one is, say, for example, in hard sphere systems we talked about, there are only two phases. One is the fluid phase, another one is the crystal phase. Okay, the fluid phase is more divided into like the liquid and gas because there is no attraction there. The liquid gas distinguishability will come only if you have attraction, or this transition happens only if there is attraction. Otherwise, you call it as a fluid phase. But so the hard sphere colloids, what we saw is okay, you have a fluid phase, you have a crystal phase. The fluid phase is not divided or into liquid and gas, and there is no transition between this. Okay, but if you have like the smaller particle also in the colloid, the hard sphere colloids things, then you have this effective attraction between the larger colloids. Then the larger colloids, you will see all the three phases. You find like the gas, liquid, and the crystal. Okay, so that way, this is one of the manifestations of this entropy-driven depletion interaction. Okay, so you can actually like there is some theory to measure like what is the interaction and so on. So it's an attraction. So this is this point is basically the surface of this colloid, and after that you have an attraction, and then this attraction is very short range, and the range is only the diameter of this particle, only that one. So you have an attraction. So it's like a sticky particle. Okay, you come very close, you get attracted. Otherwise, you are like hard sphere, like that. So this was basically proposed in 50s by Asakura and Osawa, like these two people. And then later on, I think at least for like 2-3 decades, people didn't bother much about it. But then again, it kind of like around 70s, again, the colloidal science itself become quite interesting. And then the depletion interaction also people started thinking about it. And this one, so we said that whenever two particles comes, you have this depletion layer overlapping, and then you have the effective attraction. This happens if you confine these particles in some between some walls, like where you have like for example, you have a wall like this, confined. Then the wall also has a depletion layer where the smaller particles cannot enter. And then when the bigger particles comes here, they are essentially like releasing space for the smaller particles to move around. Entropy increases. So there is an attraction between the external potential as well as the larger particles. Okay, so here again, it's a hard sphere repulsion between the wall and the particles. So even if you have a soft potential, then also this is true. So you can see from here actually, if you look at this is basically the number of particles you have, the larger and smaller particles from the wall. Okay. So you can see the larger particle there, you have a higher density there. Smaller particle, it's a lower density. That means the larger particle is getting attracted towards the wall, but smaller particle getting depleted away from that. Okay. So this is what is the effect of depletion interactions and so on. So, and then one thing which you look at here is basically all these repulsive interactions are like infinite, like hard sphere is an infinite potential and so on. But let's say if you look at some potential which is finite but repulsive, then whether we'll have this entropy driven interaction or not. So that is one question which we were asking. So this I think don't bother much about this one. This is some model which we use for the computer simulations, but I can explain it here. So what we have is we have a box in which we have a lot of particles, like bigger and smaller particles. And then this is the potential which is to confine inside the box. So that is both these sides. And in addition to that, we actually put a Gaussian potential in the middle. Okay, so this potential is repulsive. So in principle, the particle should stay away from this potential barrier because it's a repulsive potential. And then what we did is we first started with just the large colloidal particles. So only when large colloidal particles are there, you can see it gets depleted. So this is basically the density along this direction. So at the middle, you can see the density is becoming smaller. So that means this potential is actually repulsing the larger particles there. Then once we got this one, we added the smaller particles into the simulation box. So you have a lot of smaller particles also now. Now, when you have bigger and smaller particles, the depletion interaction sets into play. Okay, so then you can see if you increase the number of smaller particles, slowly you can see the larger particles getting the density of larger particles getting increased at this region. Then again, if you increase more, then you get more. Okay. So which kind of tells you that there is a depletion in the entropy-driven depletion interaction, which attracts the larger colloids, even if the potential is finite. Okay. And then this actually changes this attractive repulsion, actually changes the dynamics quite a bit. So if you look at the dynamics, actually what happens is the larger particle, you have you can calculate the mean square displacement. This is basically the fluctuation or the width of the displacement distribution. That's this one, which in the layman terms you can say this actually measures how much the particle moves. Okay. Not exactly correct, but in the layman language, you can say this is how much the particle moves in this particular time, roughly that one. And then, okay, if it's a straight line, that means that's a normal diffusion of particles. If the behavior changes from the straight line, then it's not the normal diffusion. Okay, and from the slope of this, you can actually calculate what is the diffusion coefficient, which is basically the measure of how much the particle moves, or the measure of the transport of the particles. Okay? So what you find here is, okay, we calculated it for like both large and small particles, and for the initially when the temperature is high, the smaller particles, they diffuse faster compared to the smaller particle, larger particle, which is what normally we expect. Okay, because the larger particles will find it more difficult to move around in a sea of other particles. Compared to that, smaller particles should move faster. Okay, so that's what you find around like at higher temperatures. But if you increase the temperature smaller and smaller, then at some point, okay, there is a crossover happens, and then suddenly the temperature of the diffusivity of the smaller particles start decreasing like rapidly. But this one remains like this one, which is kind of counterintuitive, because what happens here is below this temperature, the larger particle is diffusing faster. The smaller particle is getting stuck somewhere and not moving much, but the larger particle actually diffuses faster. So what happens here is, if you go back here, you can see this, right? So there is an attraction of like larger particles to this potential barrier. So whenever the larger particles comes here, it gets attracted, so it can easily jump over this and then goes. But the larger particle, especially when their kinetic energy is very small, okay, they get the repulsion from here because it actually attracts the larger particle. That means okay, effectively the smaller particle is actually getting a repulsion. So the kinetic energy is also low at low temperature. So the larger particle the smaller particle find it very difficult to jump over this barrier to go to this side. So that doesn't happen. That's why like the diffusivity suddenly decreases very, very fast. Okay? So you can see like how the depletion interaction between the larger particle and the barrier affects the dynamics of both of them. Okay, and also there are like some signatures of glassy transition, localization, and so on. I'm not going into that one. Just one more point which I want to say is normally like okay, so you were calculating it for different temperatures, the diffusivity, and how the diffusivity depends on the temperature. I think you must have learned it. Okay, this is called the Arrhenius law. So basically, if you it is like okay, easy. The diffusivity D is something like the D0 into exponential minus EA by KBT, where EA is the activation energy, should be doing this one. So if you plot log D versus 1 by T, it should be a straight line. Okay, that's what the Arrhenius law says. For the smaller particles, you actually get a straight line. Okay, and from this you can find the activation energy. Activation energy is actually the effective barrier, which we find that okay, this is more than the actual barrier we put, which kind of tells you like why the smaller particle diffusivity is good, reducing very rapidly at low temperatures and so on. So you get the straight line for the smaller particles, which is expected. Okay, but for larger particles, you don't get a straight line. Instead of that, you get something like a concave behavior kind of thing. This is called like subarrhenius behavior. You can actually there is a different equation which is called deformed Arrhenius equation. You can fit into that one and so on. So, but the point here is basically the entropy-driven depletion interactions affect the dynamics very differently for different species in a binary mixture itself. So this is again the manifestations of entropy, like in different dynamic and phase behavior of like colloidal systems. Okay. So these are some of the manifestations which I'm talking about. Okay, so I'll this one I'll stop talking about entropy. So with this quote, actually, so Einstein, he mentioned this on thermodynamics. So what he said is it's the only physical theory of universal constant, which I'm convinced that within the framework of applicability of its basic concepts will never be overthrown. Okay, so it's like what he meant is, okay, this is basically the theory which will stay forever if you are applying within the applicability of its basic concepts. So don't go beyond that one, then okay, your theory fails. And in the case of entropy, that's what happened. Like many people actually went beyond the framework of its applicability and then started interpreting it, which gives you like a very different interpretations and even wrong things. Okay, so this is what I basically want to tell you. But before ending my talk, let me spend a few minutes on the institute from which I'm coming from. So I'm actually from the National Institute of Science Education and Research, NISER. Okay. We are actually an autonomous institute under the Department of Atomic Energy, Government of India. And we are affiliated to the deemed university called Homi Bhabha National Institute, which is again the deemed university by Department of Atomic Energy for the affiliation of all its centers and constitute like all the other CIs. Okay. So these are some of the pictures of our campus. You can see that one. So this is basically I copied from our student manual. So NISER, it's established in 2007 under the aegis of Department of Atomic Energy, and it's envisaged to be a unique research institution that gives basic undergraduate science education with world-class research activities. Okay, that's basically the preface of our student manual. And the academic vision is written like this: the aim of this distinguished institute is to attract bright, motivated students, nurture them to become world-class scientists for the country who will take up challenging research and teaching assignments in universities, DA Institute, R&D laboratories, and various industries. Okay, and these are the schools NISER have. Like we are mainly catering to the basic science, so we have all the 4 basic sciences ones: biological science, chemical science, mathematical sciences, physical sciences. Then we have 2 kind of applied sciences. One is computer science, the other one is earth and planetary science. And also like okay, we have this auxiliary department, humanities and social sciences. And so we have like 7 such schools. And there is some plan which may not happen immediately, but NISER has a plan to start an engineering school. But I don't know when it will happen. Okay. And we have like a different academic programs. So this is our flagship course. This is a 5-year integrated MSc Physics, which people can join after the +2. And admission is through like what you call the NEST, National Entrance Screening Test. I think you must be familiar with NEST at least, because I know like after Odisha, the most number of people, number of students who are writing NEST is from Kerala. And we have centers, I think, in all the 14 districts of Kerala. So I know NEST is quite popular in Kerala. And also like the NEST is not only for the admission to NISER, but there is a DA center in Bombay University called Center for Basic Science. So we both together conduct this NEST. I think this year the exam is on 18th of June. You can get the details if you go to this website. So that's about the MSc 5-year integrated course. So we select about 2002 students every year in this one. And in the first year, it's a common course. So everybody has to take physics, chemistry, mathematics, biology In addition to that, you will have humanities course, which can be English, sociology, economics, and so on. And also, I think there is a computer science lab also. And we are trying to introduce some course from the earth and planetary science also into the first year. But this first year is common to all of the students. And then after the first year, depending on the student preference and their performance in the first year, their streams will be allocated. So right now it's only 4: physics, chemistry, biology, and mathematics. But computer science and earth and planetary sciences will be starting their own integrated MSc program, I think most probably next year. So then, this after first year, the students will get divided into 6 different streams. Then, the first 2 years in that one, that is your second year and third year, you will be doing the basic courses in the respective disciplines. In addition to that, every semester you need to take at least one course from outside the department. So, for example, if you are in physics, you will be doing a lot of course in physics in the second and third year. But in addition to that, every semester you will be doing one course from mathematics or biology or chemistry or computer science. So that will be. And then, in the fourth and fifth year, the courses are mostly elective. So you will be doing advanced elective courses. So you have some choice, like the department will be offering some 5 or 6 courses, and you need to choose 3 or 4 from that one and then do this one. And the final year, or some other departments from the 4th year itself, you will have a project, and your degree will be awarded only if you submit a master's thesis. Okay, so that's basically about the MSc, integrated MSc course. In addition to that, we have the PhD course. This is again the selection is, or even to apply, people have to qualify one of these exams, like GATE, JEST, UGC, or CSIR. If you have qualified in one of these exams, you can apply for the PhD programs in NISER, each department. And then each department will have their own criteria, how to shortlist these applications and so on. Then there will be, sometimes you will have a test also to shortlist. Then there will be an interview, and based on your performance in this interview, you will be selected for the PhD. And PhD is normally a 5-year program, but sometimes it can go further, more But generally, people will finish their PhD within 5 to 6 years. So, and then the other course we have is the integrated MSc PhD, which is physics has already started this course. Chemistry is starting this year, and biology and mathematics is also in the process. I think they will be starting in a year or something. So this is basically the combined masters and PhDs thing. So the students will be coming here after the bachelor degree, BSc Physics, or in the respective disciplines. And again, they need to qualify one of these exams, JEST or JAM, then only they can apply. And again, there will be an interview process, and admission will be done only after that. And here, once you go to the integrated MSc course, initially you will be doing only coursework for one year or something. Then second year onwards, you will start doing a research project. And end of the third year, you need to submit a master's thesis, and based on that, you will get a master's degree. And you continue doing your PhD. And once you finish your PhD, you get the doctorate. Okay? And this year, we have introduced this course. This is a master's program in medical and radiological physics. So again, you need to have a JEST or JAM in this one. And this is basically done by NISER in association with, I think, Tata Memorial Hospital in Mumbai, which is again a DI's institute. And also AIMS Bhubaneswar, and I think one of the other medical colleges in Bhubaneswar, they together conducting this one. And this is again basically it's about the physics behind all this radiological instruments and all those things. And they will have like hands-on sessions with these hospitals and so on. So that's a new program which we are introducing right now. So these are basically the academic programs and how you get into the admission to NISER. Okay, so this is what I want to talk about NISER. So here I'll stop. So thank you everyone.
Shajilmash, I think there are 2 or 3 questions in the box. Oh, yeah, Chen.
Okay, yeah. Yeah, I can answer that one. So yeah, it has to be science stream because you are if you look at the next question paper, there are like questions from all the 4 different basic science subjects like mathematics, chemistry, physics, and biology. So you need to be scoring a minimum marks in each of the science subjects to get into the rank list itself. So even if you do well in 3 and 1 you do very badly, then okay, you won't get into NISER rank list, but you can still get into CBS because they consider only 3. So they take the best 3, but NISER also take the best 3 for the ranking, but you have a minimum for the 4th one. So it has to be science too. Yeah, that's what I said actually. Okay, yeah. So see, so far what happens is whomever completed the integrated MSc course, I can say 90% of them have gone for PhD. And that too in mostly in universities in US, like only few actually stay back in India. And India also, like they actually get into like very good institutes like TFR, IAC, and so on. So that's what basically people were doing. Like they were going for PhD, and few people actually went to BARC itself. Like so, BARC they have this. After MSc, they have this BARC school. So there, if you get selected, then BRC or one of the units of DAE absorbs it. Okay. So for that, actually, NISER. So it's a written test, then an interview. But for NISER students, it's a direct interview. So you don't need to write the written test. You can just go for the interview and get into the one. And quite a few people actually went to that one also. So this is, and nobody actually tried for any job as such, because most of the people coming to NISER, they come with the intention of doing PhD after the integrated MSc. So they actually look for PhD only, like they don't really look for jobs. So I cannot tell you clearly like okay, what will be the job scenario. But many students of like our first 1 or 2 batches of MSc, they have now started completing the PhD, and they are getting into different jobs actually, like industry jobs and academic jobs. So many of them have, nowadays this data science is a huge thing. So many of them get into like okay, data science companies actually. That's what I'm hearing. So yeah. So that's basically like what I know. Like mostly people go for PhD, and that too mostly abroad. Yeah. One good thing about nowadays is like there are a lot of information available. You can get to know that there are all these institutes and all these courses are happening. So people can actually explore the avenues. Yeah, so basically the idea behind starting NISER and all these ICES were exactly that, like to attract more students towards the basic science thing. So yeah, I don't know, okay, but I think okay, it's kind of successful. Yes. Yes. So every batch actually we get about 20% students from Kerala. So let's say like to about 40 students from Kerala every year comes to NISER. Yeah. Yeah, so also nowadays, like many people are actually using computer simulations to study all these things. There are like quite a bit of advantages, of course, disadvantages also, because you are not doing the experiment in reality. So you do it in computer science. So whatever you are feeding to the computer, okay, it will give that only back. So, there are many people actually doing this, and many new observations and findings are coming out also from computer simulations. And yeah, also like the capability of computers have increased quite a bit. Like earlier, like doing see what molecular dynamics this is just simulating the dynamics of a group of particles. So earlier, okay, you could do maybe 100 particles or 200 particles. Nowadays, you can do millions of particles in a day or two, kind of thing. So that much. So it is actually coming up in a big way, and now especially this artificial intelligence and machine learning that is taking into the center space now. So many people are using artificial intelligence and machine learning to their research problems. And this is one of the things why the data science companies are also like becoming bigger and bigger every day. So NISER also, there are many people actually working with. And we have quite a good computational facility. So there are many faculty members and many students. They are actually using the computational methods to like explore the problems, which is.
Shajil Mash, we have got lots of veterans, here, like Jairam, PJ Bhatt, Padmanabhan, TK Sundaramurthy, and some of them. Why don't we get a
Okay, thank you. This is a very interesting topic. Dr. Anil Kumar has covered now, and he has done a lot of studies in the field, and I'm sure it will be opening the a wide area for our interesting students to venture into in research in this area, especially in thermodynamics and physics and related topics. And our children should explore these areas of research. And once they get into the institute, I would like the NISER to expand their lab facilities to do the experimentation, because computer simulations have their own limitations in exploring the computer simulation can really explore the research from a known theory, but if they want to experiment something on which is not known, physical test, lab tests are necessary, and that will definitely increase the value, attractiveness of the institution and its value. I'm sure your explanations of the theory will be very, very attractive to our young students, and they will get a higher and higher education in your institute. And I request the students to explore this possibility, especially those who are many in our group who are interested in explosions and collisions, not only the particles and also the celestial bodies. Okay, thank you very much.
Okay, can I just add one thing? So even though I'm using computer simulations, there are many labs, many faculty members, and many groups in NISER who are doing experiments. So the experimental facility is already there, so students can actually explore. Like, we don't need to expand the experimental facility; it's already existing. Only thing is, I'm not doing any experiment.
No, we space scientists do simulations.
Yeah.
So we do a lot of extensive computer simulations to prove our theory before we put it into the operations. Okay. So simulations are to prove our concepts. That is what.
Yeah, I understand.
I know there are simulation studies done all over the world, and especially in the area of physical sciences. But of course, they are also substantiated or assisted by the physical tests. That is what I was saying. So an expansion of the facilities with the laboratory will be much, much more attractive to the students and to the country itself.
Okay. Yeah. So what I'm saying is the laboratory is already there. So I'm actually collaborating with the experimentalist. I'm not myself doing the experiment. That's what.
Dr.
Okay,
Jairam,
thank you.
Dr. Jairam, please. Dr. Jairam.
Good evening. Are you able to hear me? Okay, first of all, Dr. Kumar, very good talk, I should say. Of course, it would have been very, very heavy for the students. So-called entropy, which is almost 200, 300 years old, still not understood by many people across. Not many people really work on that area at all. In fact, I had the privilege of working on entropy for my PhD thesis and remote sensing data analytics when we tried to do merging different sensors data, trying to find out information content, net effect because of the uncertainty involved in comparing data sets from different places. It's a very exciting concept, but I do believe maybe for the students at school level it may be very heavy. I was also disappointed when I see the attendance there, the dwindling attendance. In the beginning, there were so many people attended this meeting. Now I find hardly 7 people other than the seniors. Less than 16 people are attending at this particular point in time. I don't know how many of our students. That is a bit discouraging. I think we should check that component. Because Anil Kumar already make an effort to answer 1.5 hours of talk, a topic which is very, very important for analytical mind. Maybe it is not really absorbed by the students. So this is my feeling. Maybe I'm wrong. Okay. Thank you.
No, not now. Not sorry, not now.
Rangarajan, you need to say something more.
Please go ahead, Shajil Mash. I'm engaged in something else. Sorry. Please go.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.